Hello, today we're going to talk about energy and electron transitions. So you should have talked about energy a little bit in ninth grade science, whether you took P's or whether you took algebra-based physics. Either way, you should have covered waves and energy a little bit, but we're going to do just a review. So light, which is a generic term that we think of as being light that we can see, but really can be any kind of electromagnetic radiation. Can come in two forms. Sometimes it behaves like waves, and sometimes it behaves like particles. So when we're talking about light behaving like a particle, we refer to it as a photon of light. So a photon is a particle of light energy, basically. So today I'm going to show you, or we're going to talk about the relationship between that wave and the energy of the particle, because sometimes light is kind of weird and sometimes it switches its behavior in the middle. It's not like it's always a wave or always a particle. Its behavior can't really be explained completely by either one, so we have to use both to explain it. All right, so this diagram should look familiar to you from previous science classes, but basically light, if it's behaving like a wave, then we have the wave going up and down. If it has a high frequency, meaning there are a lot of waves per second or per unit time, then it will have a short wavelength, right? The wavelength has to be short if we're going to fit a lot into a given period of time. All right, and so if we're thinking about energy, the more you get per unit time, the higher your energy will be. All right, so high frequency is high frequency waves will give you high energy photons of light. And then the same is true for the wavelength being short. So energy and frequency are directly related, and wavelength is inversely related to each of them. Okay, just as a frame of reference, because I feel like it's helpful, the higher energy light that we can see is going to be near the violet section of the visible spectrum. You can hopefully it can help you remember this because it's right next to the ultraviolet, which we can't see, but you should know from experience is slightly higher energy because it's slightly more dangerous, right? That's what gives us sunburn in the summer if we're out in the sun for too long. And now the opposite is also true. If we have longer wavelengths, we get fewer in a given time period, and so that will be lower energy. All right, that end of the visible spectrum is going to be red, which is right next to the infrared, which is what we use to keep fast food warm and things like that. So it's not as high energy as the ultraviolet on the other side. All right, in this unit, we will use the Bohr model a lot. It is an imperfect model of the atom, so we talked a little bit in the last unit about how electrons are really in a cloud. But Niels Bohr observed that electrons could only be present at certain energies, all right? So that means it is, or the word we use for that is quantized. So quantized energy means there's only specific values of energy that are allowed. So one way to think about this is in terms of potential energy, right? If you had, you probably learned back in physics that, if you have a ball at a higher height, it has a higher potential energy because it has further that it could fall, right? So this would be like, it could be on one shelf or a second shelf or a third shelf, right? There are only specific places that it can be to have specific potential energy values. Whereas if it was continuous, you'd be able to put it anywhere vertically in space, and that would be a continuous energy. So for the atom, our potential energy is related to the attraction to the nucleus. So closer to the nucleus is going to have a lower potential energy because we have that attraction between the electron and the protons in the nucleus, right? As we move out, it requires energy to pull that negative charge away from the positive, and so the potential energy will get bigger as we move farther from the nucleus. So he often describes these are referred to as energy levels. So the first orbit, which we know is not actually an orbit, it's part of the cloud, but the first level has the lowest potential energy, and second, third, and so on as you go out. And this is the model we often use, and we'll use bingo chips to represent the electrons later in this unit. But I just wanted to mention that in reality, as you move out, the difference between the levels gets smaller. So there's a much larger energy difference between levels 1 and 2 than there is between levels 5 and 6, for example. All right. So that will be more important as we get to how we can see the transitions that happen within the atom, which will be our next lesson.